Strength, endurance, and precision engineering define how Sonico builds its next generation of leaf springs. Each unit carries the weight of performance vehicles around the world, and every detail in its creation reflects both power and purpose. What stands out most is the consistency achieved through robotic control and advanced automation that feels almost alive in motion. And production opens with high-capacity steel shearing, cutting raw bars into exact profiles before drilling and hot punching create anchor points for assembly. Gas-fired furnaces heat the ends to achieve superior surface retention, and parabolic rolling machines form the signature curved profile with servo-controlled accuracy. Descaling removes oxidation, keeping the surface clean for flawless shaping. Multi-station presses streamline the process, avoiding repeated heating and preserving strength. The harmony between temperature control and mechanical force here is a true mark of technical mastery. Die rolling and reaming shape the spring ends, preparing them for robotic heat treatment. Two automated arms transfer each leaf swiftly from the furnace to the cambering press, minimizing air exposure. The gas-fired furnace ensures uniform heat distribution, while real-time temperature sensors monitor each leaf to maintain microstructural integrity. An inline straightening unit corrects any lateral bends in longer leaves, ensuring perfect alignment. This section shows just how vital timing and temperature synchronization are to maintaining top-grade resilience. Next comes stress shot peening. Turbine-powered streams of steel shots strike every surface twice, enhancing durability through compressive residual stresses. The online sieve shaker keeps particle sizes consistent for controlled impact distribution. This dual-pass treatment gives every spring a toughness you can trust, especially under extreme load conditions. NTHE painting line follows, using electrostatic bell applicators within a dust-free chamber to achieve even coating and strong adhesion. Conveyorized assembly then connects each component through hydraulic clamping presses, avoiding hammering for smoother finishes. CNC-controlled scragging calibrates load and deflection, while computerized grading ensures each leaf meets design tolerance. The integrated inspection station certifies every detail before shipment. This seamless combination of robotics and human oversight captures the essence of industrial evolution. NNN.
The production process of steel lifting slings begins with sourcing high-grade steel wire ropes, which are imported from Asia. These materials are then cut to the required length, in this case, 61 meters by 0.36 meters, and subjected to a rigorous splicing and pressing process to form secure loops. Precision machining ensures uniformity, while strict quality control measures verify load-bearing capacity and safety compliance. The slings are then coated for corrosion resistance before being delivered just in time to meet deadlines, ensuring efficient supply chain management and seamless integration into operations. This is the world's longest cable-laid slings with 280-meter length. Its production process begins with the selection of high-strength steel cables, which are arranged in a helical pattern to form a cable-laid structure. Once the main structure is formed, skilled technicians hand-splice soft eyes at both ends, a complex technique that enhances the sling's flexibility and load-bearing capacity. The splicing process requires expert craftsmanship to maintain structural integrity and ensure durability under extreme loads. After splicing, rigorous quality control measures are conducted, including dimensional inspections, tension tests, and load-bearing evaluations, to verify the sling's compliance with industry standards. These tests ensure the slings can withstand the heavy loads and harsh conditions of offshore operations. How the Bronneberg Super 2 scrap baler works and its role in the recycling industry. The Bronneberg Super 2 scrap baler is a highly efficient and reliable machine designed to process and compress scrap metal into dense, manageable bales. This baler is widely used in the recycling industry due to its robust construction, low maintenance costs, and high efficiency in handling various types of metal waste. With a reputation for durability and performance, the Super 2 has gained popularity among recycling businesses worldwide. The machine operates with a large compression box, which can be equipped with or without a front loader for easier material handling. Scrap metal, including steel, aluminum, copper, and mixed metals, is loaded into the compression chamber. The hydraulic system then applies immense pressure to compact the scrap into high-density bales. The fully serrated wear plates inside the chamber prevent material slippage, ensuring even compression and prolonging the machine's lifespan. This design reduces operational costs and enhances overall efficiency. Once the metal is compressed, the machine forms it into uniform bales. An automated ejection system then pushes the finished bale out for storage or transportation. These bales are ready for direct melting in smelters, significantly reducing processing time and transportation expenses. By compacting scrap metal, the Bronneberg Super 2 baler enhances recycling efficiency, allowing companies to handle larger volumes of scrap while optimizing their workflow. The Bronneberg Super 2 scrap baler plays a crucial role in the recycling industry by making metal processing more efficient and cost-effective. It reduces scrap volume by up to 80%, making storage and transportation more manageable. The machine is capable of producing 10 to 30 bales per hour, depending on the type and density of the material. Additionally, recycling compressed metal contributes to a 60 to 90% reduction in energy consumption compared to primary metal production, making it an environmentally friendly solution. One of the key advantages of the Super 2 baler is its durability and low maintenance requirements. Built with high-quality components, it offers an extended operational life with minimal downtime, ensuring maximum return on investment. The fully serrated wear plates and heavy-duty construction make it a long-lasting and cost-effective solution for metal recyclers. Investment casting, also known as lost wax casting, is a precision manufacturing process used to create complex metal components with fine details and tight tolerances. The process involves multiple steps to ensure high-quality final products. Pattern assembly. Wax patterns are created using injection molding and assembled onto a sprue to form a pattern cluster. These patterns represent the final metal components and will eventually be replaced by molten metal. Ceramic mold formation. The assembled wax patterns are dipped into a fused silica slurry to create the initial ceramic coating. This coating captures fine surface details. After dipping, stuccoing is applied using fused silica particles to build additional layers of ceramic. Mold strengthening. The mold is built up through repeated cycles of dipping and stuccoing, typically forming 7 layers of ceramic. Once fully coated, the molds are left to dry and harden. Wax removal. The ceramic molds are placed inside a pressurized steam vessel to remove the wax. The process takes approximately 15 minutes at 120 psi, ensuring complete removal of wax while maintaining mold integrity. High-temperature firing. After wax removal, the molds are fired at 1,800 degrees Fahrenheit to strengthen the ceramic shell. This step also eliminates residual wax and prepares the mold for metal casting. The fired molds are then set into pouring beds. Metal melting and pouring. 304 stainless steel is induction melted at 3,000 degrees Fahrenheit and poured into the preheated ceramic molds. A slag rod is used to remove non-metallic impurities from the molten metal before pouring to ensure material purity. Casting, removal, and finishing. Once the metal has solidified, the ceramic shell is broken away, and individual cast parts are removed from the sprue using an abrasive cutoff process. Further refinements, such as CNC grinding, are performed to remove gates and improve dimensional accuracy. The 9x19mm case press is a vertical transfer press designed to transform brass cups into non-grooved cartridge cases. It operates by feeding pre-formed brass cups into a series of stations within the press. Each station performs a specific forming task, such as drawing, stretching, or shaping, using a combination of punches and dies. The vertical design allows for precise alignment and efficient transfer of the workpiece between stations, typically via automated mechanisms.
Industrial machinery transforms solid steel blocks into components of exacting standards. The facility harnesses mechanical power to mold raw material with exacting specifications, pushing metal through successive dies until shapes meet strict engineering requirements. Every forging press is calibrated to apply consistent force, ensuring each piece meets design specifications. Skilled technicians monitor subtle variations in metal behavior, adjusting parameters in real time. Each strike of the forging press refines form and density, ensuring durability for demanding applications. The controlled environment allows for continuous monitoring of temperature and alignment, preventing defects before they emerge. Operators coordinate sequences that maximize efficiency while maintaining quality standards across all pieces. Automation aids in synchronizing movements between multiple presses, reducing cycle times without sacrificing quality. Forging machines drive the metal through preheating stations where heat enhances malleability, preparing blocks for precision shaping. Lubrication systems reduce friction during forming, extending tool life, and maintaining surface finish. Next, billets pass to the main press, where hydraulic systems apply immense force to achieve the desired geometry. Multiple stations manage intermediate adjustments, guaranteeing uniformity and eliminating stress points that could compromise structural integrity. Post-forging thermal treatments further stabilize the metal's microstructure, enhancing mechanical performance. Once the final shape is achieved, components are inspected using advanced measurement tools to verify tolerances and surface quality. Every inspected piece contributes to the reliability of machinery in critical industries, reflecting decades of engineering expertise using in tools.
The Rajendra Extra Heavy-Duty 30-feet lathe machine with a 60-inch center height is designed for machining large crankshafts with precision. The crankshaft is securely mounted between the headstock and tailstock, with steady rests providing additional support to prevent deflection. The machine's high torque motor ensures smooth rotation, while the robust carriage and tool post allow controlled cutting operations. Rough turning, semi-finishing, and finishing cuts are performed using carbide or high-speed steel tools. Specialized attachments, such as offset fixtures or follower rests, help maintain accuracy. The machine's rigidity and precision feeds enable efficient material removal, ensuring the crankshaft meets exact specifications.
What allows a single machine to complete complex shaft components in just one operation? The Hyperturn 65TT triple turret CNC machine handles complete machining of shaft-type components in a single setup. Steel bars, up to 95 mm in diameter, are loaded and secured in the live center turret. The dual spindles rotate with controlled precision, while up to 36 driven tools, supported by 3 Y-axes, engage the material. Each turret moves with synchronized timing, allowing roughing, shaping, and finishing operations without repositioning the component. Steady rest units stabilize the workpiece during high-speed cuts, minimizing vibration and ensuring uniform tolerances. The Sinumeric 840 DSL CNC system monitors all motions, automatically adjusting feeds and speeds to maintain consistent quality. Operators supervise via the Operate user interface, optimizing cycle times and preventing errors. This integration of advanced control, multiple tool positions, and dual spindles turns raw steel into precisely machined components efficiently. It's a true testament to modern engineering ingenuity. The level of synchronization and automation is astonishing. NN.
At Sunmark Stainless, strength takes a seamless form. Behind each stainless steel tube lies a chain of precision operations that turn raw coils into products built for performance, consistency, and endurance. What truly stands out here is how every mechanical stage interlocks like a living system. No wasted movement, no hesitation, only purpose. End production opens as stainless steel coils are uncoiled and leveled, setting the base for tube formation. Each strip is slit to the required width using high-speed slitting machines before being fed into one of 9 advanced forming mills. The rollers gradually curve the flat strip into a perfect circular shape. High-frequency induction welding then fuses the edges with controlled energy, forming a strong, continuous joint without filler material. This seamless fusion defines not just durability, but technical brilliance born of mastery. NTHE welded seam undergoes bead rolling and scarfing, removing any excess material to create a smooth inner and outer surface. Tubes then pass through sizing and straightening sections to achieve the exact outer diameter, ranging from 19.05 mm to 76.20 mm, with thickness between 0.9 and 2.5 mm. Automatic cutoff machines trim each tube to lengths from 3 to 6.2 meters. There's something satisfying in knowing each cut translates to dimensional perfection, tuned by machines built for reliability. Next comes finishing, a hallmark of Sunmark's stainless identity. Depending on customer requirements, surfaces are polished to 180 number, 320 hash, 400 hash mirror, or even 600 hash mirror finish. Specialized polishing heads ensure a uniform grain direction and gloss level, giving the tubes not just shine, but measurable smoothness critical for their industrial and architectural use. That level of refinement gives the product its character, engineered, not embellished. Every batch is tested to meet ASTM A554 and equivalent EN standards. Eddy current inspection checks for micro defects, while mechanical and dimensional tests confirm integrity. Tubes are finally packed with protective film and stacked for shipment. The discipline in these closing stages shows how industrial craftsmanship can feel almost like an art of repetition done flawlessly.
This section is about bending an 80 mm thick S355 steel sheet with a length of 2,500 mm using a high-capacity press brake. Due to the material strength, specialized V dies and a powerful hydraulic or mechanical press are essential. The process starts with calculating the required tonnage and selecting an appropriate bend radius to prevent cracking. The sheet is positioned accurately, and gradual force is applied to achieve the desired angle. Given the thickness, multiple passes or preheating may be necessary to reduce stress. This is a tandem press brake for street pole manufacturing, a specialized machine designed to bend and form large metal sheets into tapered or polygonal poles. This system consists of two synchronized press brakes working together, allowing for the efficient processing of long and heavy workpieces. The tandem configuration ensures uniform bending, which is essential for producing high-quality street poles with consistent shapes and dimensions. The DA52 control system plays a crucial role in operating the machine with precision. It allows operators to input bending sequences, angles, and force parameters, ensuring repeatability and accuracy in each bend. The system provides real-time monitoring and adjustment capabilities, minimizing errors and improving efficiency. With this advanced control system, the press brake can execute complex bending operations with minimal manual intervention. An automatic front feeding system is integrated into the machine to enhance productivity. This system automatically moves large metal sheets into the bending area, ensuring precise positioning before each bend. By reducing manual handling, the feeding system not only increases efficiency but also improves worker safety and reduces production time. The Y1 and Y2 axis control independently manages the left and right hydraulic cylinders of each press brake, ensuring perfect synchronization during bending. This feature is critical for handling large workpieces, as it prevents misalignment and deformation. The tandem operation allows for multiple bends along the length of the metal sheet, gradually shaping it into the desired street pole form. Once the bending process is complete, the formed pole sections are moved for further processing, such as welding and finishing.
Wire rods evolve into high-strength iron rods at United Steel Company, crafted to comply with British Standard 4449. Hot-rolled and cold-rolled coils feed the production line. Rods are cut, shaped, and galvanized as required. Pipes and fuel tanks are fabricated on demand. Each stage integrates careful handling and testing to meet strict quality standards. Observing the workflow emphasizes engineering efficiency and product reliability.
The hot rolling mill roars to life, turning raw steel billets into seamless lengths of strength and structure. Each moment inside the plant is powered by synchronized motion, where 11 rolling stands form the heart of continuous production. Every pass through the mill tightens tolerance, shaping metal with astonishing accuracy. The process reflects decades of experience engineered into performance and reliability. NTHE Journey opens with billets heated to extreme temperatures inside the reheat furnace. Their surfaces glow red-orange as they reach rolling temperature, soft enough for deformation but still dense with strength. Hydraulic feeders then push them forward to the roughing stands, where the first reduction in size occurs through heavy rollers applying immense pressure. That force transforms solid blocks into dynamic forms of motion and heat. The combination of temperature and mechanical force defines how efficiently each billet evolves. Next comes the intermediate rolling stage, where the elongated billets travel rapidly through several stands, each one fine-tuning the profile. Sensors monitor temperature and thickness in real time, ensuring uniform results through the entire length. By the time the material reaches the finishing stands, it has achieved its desired dimension and surface integrity. Every revolution of those rolls represents pure control over industrial power. This stage truly reveals the harmony between technology and engineering expertise. NTHE steel exits the final stand and passes through cooling beds, where controlled air and timing deliver consistent hardness. Straightening units align the bars precisely before automatic shears cut them into predetermined lengths. Finally, a fully automated conveyor system carries the products to bundling and inspection stations. Each finished bar embodies a balance between science and raw force. This entire sequence shows how machinery and expertise together forge the language of strength.
Specialty steel forged rolled process. The specialty steel forged rolled process is a precision-engineered manufacturing method that enhances the strength, uniformity, and internal soundness of large steel bars. The process begins with an as-cast ingot, which is heated in a soaking pit until it reaches a consistent temperature. Once uniformly heated, the ingot is transferred to the forge press, where it undergoes high-pressure deformation. The forge press applies up to 3,300 metric tons of force, compressing the ingot along its entire length. This controlled multi-pass forging process refines the internal grain structure, eliminating voids and enhancing the center soundness of the steel. The repeated forging passes ensure uniformity and improved mechanical properties, making the steel suitable for demanding applications. Following forging, the semi-finished steel moves to the rolling mill, where further shaping and size refinement occur. The rolling process ensures precise dimensions, consistent weight, and tight tolerances. This combined forging and rolling method produces high-performance steel bars with superior reliability, meeting the stringent demands of industries worldwide. The result is a stronger, cleaner, and more consistent specialty steel product for critical applications. Roles of forging machines and CNC machines in industrial production. Forging machines and CNC machines play vital roles in modern industrial production, enhancing efficiency, precision, and scalability. Forging machines shape metal by applying compressive forces through hammering, pressing, or rolling. They are widely used in automotive, aerospace, and construction industries. Forging improves material strength due to grain refinement, resulting in products that are 20 to 30% stronger than cast or machined components. Large-scale forging presses can exert forces up to 50,000 tons, enabling the production of crankshafts, gears, and aircraft components. Industries rely on forging machines to produce over 18 million tons of steel forgings annually worldwide. CNC machines use computer-controlled tools to cut, drill, and shape materials with extreme precision, often reaching tolerances as tight as plus or minus 0.002 millimeters. These machines are crucial in industries like aerospace, medical device manufacturing, and electronics, where complex and high-accuracy components are required. The global CNC machine market was valued at $86 billion in 2022, reflecting its massive industrial significance. CNC technology enhances automation, reducing labor costs by 30 to 50% while increasing production speed. Advanced CNC machining centers can operate 24/7, producing thousands of components with minimal human intervention. The modernized bar mill at Hyundai Steel utilizes a 3-roll precision sizing mill, PSM, to roll special bar quality grades with high precision. The process begins with billets heated to rolling temperature, which then pass through 14 mill stands for roughing and intermediate rolling. The 3-roll PSM ensures smooth, round dimensions, eliminating frequent roll changes. The hydraulic adjustment, controlled by the technological control system, allows on-the-fly modifications. The automated system ensures uniform quality, while quick roll changes minimize downtime. Finally, finished bars are cut to size and cooled, meeting stringent automotive industry standards. This modernization enhances efficiency, precision, and market adaptability.
Steel billets enter the 6,500-ton hot forging press, undergoing extreme force under tightly controlled temperatures to form high-performance crankshafts for automotive engines. Each billet is carefully positioned, and the press cycles are adjusted based on material behavior to ensure uniform deformation and symmetrical geometry. Forging dies are engineered for durability and repeatability, allowing continuous high-volume production while maintaining consistent quality. Operators closely monitor heating, alignment, and metal flow, making real-time adjustments to prevent defects and ensure optimal grain structure. Forged blanks progress through secondary forging stations, where critical features such as journals and crank pins are precisely shaped. Advanced sensors track temperature and pressure, confirming uniform material flow and structural integrity. Controlled cooling follows forging, stabilizing the internal structure and reducing residual stress in the metal. Each stage of the forging sequence emphasizes mechanical properties and dimensional consistency. Engineers oversee the process to guarantee that each crankshaft meets the demanding requirements of modern engines. The combination of immense mechanical force, careful monitoring, and precise die design ensures that every forged crankshaft attains the strength and reliability required for high-performance automotive applications.
Under the heat of McAllister Industries' high-temperature system, a block of stainless steel reaches its target temperature of 1,950 degrees Fahrenheit. A thermocouple is attached directly to the metal, transmitting every degree of change to a chart recorder that traces a precise thermal history. Once the targeted temperature is achieved, the furnace door opens, and the part is transferred swiftly toward the quenching station. The transition must happen in seconds to maintain metallurgical integrity. As the steel is submerged in the water tank, heat energy dissipates instantly, locking in strength and durability through rapid contraction. Engineers observe the data curve, confirming the temperature drop aligns with treatment specifications. The process ensures uniform grain structure and stress relief, preparing the component for future tempering or machining. Before the next cycle, technicians verify the equipment's calibration and inspect surface finish for signs of distortion. Every sequence demonstrates mastery over heat, timing, and transformation, industrial expertise at its core.
Glenfield Valves crafts and assembles industrial valves with exacting standards. Automated systems, modular components, and controlled coating ensure durability. PLC-controlled testing verifies pressure and flow, while operators adjust for valve type. Each unit undergoes strict quality checks, delivering reliable, long-lasting performance worldwide.